Well, it's about time that we started talking about circles. And neutrally speaking, we have not talked about a circle. Triangles, quadrilaterals, polygons, area, nary a circle to be found. Let's make sure that we all know what we're talking about when we talk about a circle. A circle centered at some point O. A circle, the normal definition of a circle will do just fine. It's the locus of points, a fixed distance from a fixed point. So when we draw a segment with endpoints, one at the center and one on the circle, that is a radius. When we draw a segment with endpoints on the circle, that is a diameter. When we draw a segment with endpoints on the circle passing through the center, that's a diameter. When we draw a segment with endpoints on the circle, that's a chord. When we draw a line that intersects the circle once, that's a tangent. And when we draw a line that intersects the circle twice, that's a secant. So for me, the colors are helpful. You will prove that in the discussion time, that if a line hits the circle, it hits the circle no more than twice. Clearly a circle can hit a line once, clearly a circle can hit a line twice, but a line may not intersect a circle in more than 2 points, and you will prove that. I'm going to prove a theorem, and we'll be okay. We're going to let T be a line. Gamma, a circle centered at O of radius R. That's going to be a circle. And P in T intersect gamma. So P is on the line T and on the circle gamma. T is tangent to gamma at P if and only if OP is perpendicular to the tangent line. And it's a biconditional, so we'll go both ways. We're going to go this way first. We'll assume that T is a tangent line, which means that it intersects the circle just once, and it intersects at P. So we will assume that that's the scenario, and we will prove that OP is perpendicular to the tangent. If OP is not the perpendicular to the tangent, then you can drop the perpendicular to the tangent. I'm sorry, yes, you can. You can drop the perpendicular from a point to a line. You can do that. So what we do then is we say whatever distance PQ is, go that distance by the ruler postulate on the other side of Q from P and draw in point R. So now you have triangle OQP and triangle OQR. Now here's the kicker. Triangle OQP is congruent to triangle OQR. And what does that mean? This implies that OR is congruent to OP. And if that's the case, then R is on gamma. Because OR would be a radius, would be a radial length, as OP is a radial length, which puts R on the circle. And if R is on the circle, T is not a tangent. And that's a contradiction. So if T is the tangent line at P, then OP must be perpendicular to the tangent line. We'll go the other way. We'll assume that OP is perpendicular to some line T. We'll assume that. And we'll prove that T must be a tangent line. How do you prove that something is a tangent line? Well, tangent lines intersect once and only once. So we imagine what would happen if this line intersected the circle again. If it intersected the circle again, it would do so at some point R that was the same distance from O that P was. And if that's the case, then triangle OPR is isosceles with two right angles. And that's just all sorts of contradiction. So the thing that you learned in Euclidean geometry is also true neutrally. Wherever the tangent intersects the circle, there's a right angle there, and that's true neutrally. Okay? Cool. That's enough. We'll talk about inscribing and circumscribing in the next video.